Hi everyone and welcome to a video on pointers. Awesome topic. A lot of the times a lot of people have trouble with it, and it's because they don't understand the basics of pointers. And if you don't get the basics as it grows, things get iffy. And also pointers, they also introduce the idea of a program crashing when you screw up things with pointers. So that discourages a lot of people. So today's job is to introduce you to pointers, give you some basic examples, maybe get into a little bit about allocation and deallocation, and then just kind of wrap it there and we will build upon that, okay? So before that though, I'd like to not introduce you, but remind you of how your computer works at home. So your computer at home is made up of a couple of components, right? So, at the heart of it, we have the CPU, right? And that CPU lives on the motherboard of your computer. All right, so there's our CPU, and there's your rig, as they call it, your box, or your machine. And in here is the motherboard, right? Now, there's another thing in the motherboard that basically one of the main jobs of the motherboard is to connect all the components, right? So just imagine that you have your motherboard there, and one of the big components that your CPU is connected to via the motherboard is going to be your RAM, right? So your RAM sticks, whether you got 2 or 4 sticks of RAM, and you've got 16 gigs of RAM, 32 gigs of RAM, etc., etc. Another major component of your computer is going to be the secondary storage. So this we call main memory for RAM. Secondary storage is going to be also connected via your motherboard, but then also to like some SATA port or something, or PCI Express. Is going to be either a hard drive disk as your secondary storage, or maybe an SSD, or even a variation of the SSD with like the NVMe drives, so solid state memory in general. Okay, so those we call secondary memory or secondary storage. In addition to that, you might have also like your GPUs, etc., etc. So you could have other components in there, but the main things are going to be your CPU and your memory, main and secondary, and then your I/O devices, of course, which are going to be your monitor for output, and then for input you got your keyboard and mouse. And of course also output could be your speakers or your audio jack for the headsets, right? Microphone for input too. So yeah, microphone. Okay, so that's basically how your computer works. Okay, and so bring it back home to what this class is about, which is programming and creating variables and objects and classes and all these things. Think about what you do when you create a variable. So when I go in and I say int x gets 5, what is happening here? Okay, what's happening there is your code, when it's being executed by the computer, the operating system gets a command from your code saying, hey, hello, Mr. or Mrs. Operating System, I guess. I would like you to give me access to some space in your storage, hopefully main memory, but I don't have control over that. I just say I want some space to store an integer. An integer happens to be 4 bytes. Now, who decides that? Well, when you're compiling your code, that gets decided. So I suppose that's already decided at that point, okay? When you compile your code in your computer, it gets decided that an integer is going to be 4 bytes, okay? So you say, I would like to have, please, 4 bytes of memory. And also, because this is one line of code, I would like to store in that 4 bytes the specific binary value representing a 5. Now, what is that going to be in binary? Well, 1 is 3, so 1 4, so it'll be something like 101, right? I believe that's 5 in binary, right? So 1 0 1 1 0 3 4, yeah, 5. Okay. And there's going to be a bunch of leading zeros here because 4 bytes is going to be 32 bits. So that's going to be 32 digits that you can put in there. That could be zeros or ones, I guess. So bits. So because you're only really using these 3, then 29 zeros are going to be there. Like there's going to be, imagine there's 29 zeros. I have 4 there, but just imagine there's 29. Okay. And that's what it looks like. So your main memory, is basically being connected by the operating system and saying, hey, I'm going to reserve this spot for this person to use for this variable called int x. Now, UCD index, your programs use it, but like internally, it's just a location in memory. So how is memory kind of organized? Well, memory is organized like a massive array. Think about like an array as you know in programming, but just like massive, okay? Now, how big are we talking about? Well, if let's say that we have a 4 gigs of RAM, that's 4,000, sorry, not 4,000, 4 billion bytes that you could have in main memory, right? So, because I mean, 4 megabytes would be 4 million. So 4 gigabytes would be 4 billion, right? So that's 4 billion bytes. Now, your memory is typically addressed in increments of 4 because each sort of address has 4 bytes in it. So what this really means is that you have 1 billion addresses that you can store information in. So think about an array of size 1 billion. Okay, so like think about 0 and then all the way to, since we started at 0 there, then it's going to be like 3, 9, 9. Oh, sorry. Be 999, 999, 999. Okay, so those are the addresses you have in just massive array. And each of these has, you know, a slot for 4 bytes. And of course, each byte is going to be 8 bits. So you could fit in 8 zeros here, 8 zeros here, 8 zeros here, or 1s, I mean, or there, okay? So that's how your memory is addressed. Now, because this is such a big number, and of course, computers deal in binary, right? So the number is actually stored in binary. So the addresses themselves are binary. So, you know, this is 0, 1, 1, 0, 1, 1, and so on. And whatever this number is in binary is what we stored there. That also decides, you know, how big of an addressing system you need. Like, because you're storing the number 1 billion there, then you could store that in a integer, right? So you really only need 32 bits to store an address, right? Because you in the 32-bit system, if it's unsigned, you could store up to 4 billion. So that's all good, because that's the other thing. When you're addressing, you could do it like this, how I have it, but how it really turns out to be done is that if you have like a, you know, if you have a really small system that only has like, 12 bits of memory, I guess. Well, actually, no, 12 bytes of memory. Let's just say if you have a system that only has 12 bytes of RAM, then because each one fits 4, the first addressing will be address 0, but then the next address is going to be address 4. Okay, because this is technically 0, 1, 2, 3, 4. You have 5, 6, 7. So the next one's going to be at, so it's 4, 5, 6, 7, so 8. And then you're good to go. Okay, so the addressing system, you know, assumes that each spot has 4 slots, so it increments in 4. Okay, so these will be the 3 addresses that you have access to, 0, 4, and 8. Okay, so going back to your 4 gigs of RAM, that means that the addressing is going to work the same way there. It's going to immediately go into address 4. And the last address you're going to see there would be the equivalent to the number, which is why I already wrote it, of 3,999,999,999. Okay, and whatever that equivalent is in binary. To store that number, you can store it in a 32-bit value, right? Because it's an integer and it's unsigned. You could do it like that, and you would have no issue there. Okay, so that's also the reason why when you have a 32-bit system, the biggest memory you can have is typically 4 gigabytes, because after that, problems arise when it comes to addressing. You need a bigger addressing system, so a 64-bit system, which is why not. That's what the common usage is. You're going to learn more about this stuff when you take CS219. I do have the entire playlist for that class because I did teach it over the summer a couple of years ago. So you're more than welcome to explore those videos if you want to find out further. But the last thing I'm going to say about memory for now is that while it is kept in binary, it's a lot easier to communicate to somebody what the address of a certain variable is by using hex code or hexadecimal. Hexadecimal is just like binary, it's just a different numbering system, but instead of being a base 2 with binary, you have base 16, which means you have 0 through 16 as values. But because we want to use single symbol values to represent those numbers, from 0 to 9, we can just use the numbers that we already have, 0 through 9. But instead of having 10 as 2 digits in binary, in decimal, with hex, we can just use a new symbol, which we just decided, like the letter A, right? So in hex, when you say 0, 1, 2, 3, 4, all the way to 9, instead of saying 10, we're going to just say the letter A, B, C, D, and E, which represents 10, 11, 12, 13, 14, and then F, which represents 15, okay? Because we like to keep single symbol for a number in base 16, just like we have base 10. You know, we don't, it's like, imagine if like the number 9 required 2 symbols to do. That would just be weird and annoying, right? We have one symbol that we got to do, which is just this little squiggly line. Well, not squiggly, it's like a circle with a line, right? But it's one stroke of movement per se. So, in fact, my 4 and 9 look very similar there. But yeah. So that's usually what you see addresses represented as. Now, because we don't want to confuse somebody, and imagine that I go ahead and say, oh yeah, I'm going to put this as address 10. This could represent 10 in binary, or sorry, in decimal. It could represent 2 in binary, and in hexadecimal, it represents 16. So actually, no. In hexadecimal, this represents. Oh yeah, 16. It does represent 16. So you can see that depending on the base of the number, it can represent a lot of things, right? So when you're seeing a hexadecimal address system and use in your computer, what you usually see is a 0 and an X followed by the hex value. So if you see something like this, you know that this is actually base 16 and represents the same thing as number 16, or the number 16 in binary, which would be maybe this, I don't know, 5, 4, 8, so I guess maybe 1 0 less. I think that's 16 in binary. I don't feel like counting right now, but yeah, the point is, you know, you got to make sure you understand that when you see 10 there, that's not a 10. That's actually hex 10, which is actually 16 in base 10. And the way you know is because it is led by this. And you'll see this later today or next time when I start running some code and I start printing addresses out. You'll see the 0x printed out. Okay, so that whole spiel I gave you is kind of leading up to the addressing system is being kept in hex. Okay, so one last thing that I have here that I want to show you. And this one, I'm just going to go ahead and import a drawing that I had. This is what it might look like in memory. So this is just representation of RAM. We can see here that we have, and there's also like a concept of virtual memory versus physical memory, and all these things I'm skipping. So like I said, there's a lot more you're going to learn. And this is actually beyond even 219. There's 370, which is the operating systems class, which goes even deeper into this stuff. So obviously I can't cover that in 5 seconds or 5 minutes or 5 hours even. So don't worry if some of this is kind of just going over really quickly. You will learn it in time. Okay, but yeah, so here we have some addresses. As you can see now, I'm using the hex representation. So I could say address 10, but we know that's not really 10 like we know. This is actually 16 because it's based 16. Same here. This number here looks like 110, but it's not. It's whatever 110 in hex is. So what would that be? If you ever want to check, you can here. Let me just switch over to screen share. So I'm on Google. There's Hexadecimals. And then go to any of these links like this one, and you can very easily convert a number. So like 110, convert to decimal. It's 272. Here's the binary representation of that. Here's some examples of how to do that by hand, which you probably learned if you took CP 100 or one of those classes. While we're at it, let's see if we had this right with the 16. So decimal 16. So yeah, 4 zeros. So is that what I had? Yeah, 4 zeros. So yeah, I had it right. The trick for the zeros is you just like, it's the location, right? So the first one here, that's a 3, technically, when you think about it. 0, 1, oh sorry, it's a 2. It's a 2, and then the next spot over is the next power of 2, which is 4. And the next spot over is power of 2, which is 8. And the next spot over is 16. So if I added an next to 0, this will be the representation of 32. You can see it by me just putting in here 32. What would that be in hex? That would probably be a 20. Yeah. So you can see there, it's just 1 extra 0. And if I want to know what 64 is in binary, I just add another 0. Now, if you ask me what like 72 is, then I have to add things together and do the math, which is what they're doing here. Okay, but this is very nice. It also works in other directions. So if you want to go from decimal to hexadecimal, so like what is that number in hexadecimal? Well, that number has a B, an E, a 9, and a 3. So what does that mean? Well, this B represents, if we look at our thing here, 11. So this is 11. And then the E represents a 14. And then the 9 and 3. So it's a pretty big number when you think about it in hex, because every time one of the digits changes because you go up by 16. So if this is 11, it means I have to go up by 16 11 times. And then for this one to be E, it had to go 16 times. For the number 15, it would be 15 times 16. So that's, you can kind of see that here when they do the multiplication. Obviously, again, I don't want to go over this, but there is very easy formulas that you can do this and convert, or you can just Google it like I did, right? Again, you don't need to do this by heart, I guess. Okay, so, all right. Now we know that addresses are kept like this, and now why am I saying all this? Because so far, all of this has been happening behind the scenes for you. You say int x equals 5, and the computer says, there you go. And you don't know anything. You in a way, you got a little bit of data abstraction going on there. You don't know that behind the scenes, what's happening is the operating system is getting an address, so it's getting one of those hex addresses. Somewhere in here, you have no control over that, actually. So like, you could just get randomly this spot right here. You have no control over that. And you don't even see what that address is right now. You simply know it as X. And internally, the system knows that X kind of goes there. So it's like, imagine like, well, I was going to say an example, but that one doesn't, I think you'll be more confused. I was going to say, think about it like websites, right? You type in google.com, but that's not the real address. It has to do a domain name lookup to see what the actual IP address is of the Google server, right? But I don't know if that's a good example, because I don't know if you guys know how that works. So I think a better example would be an operator. So like old school operator from back in the days, like way back, for like if I was born or anything, like they would call an operator and be like, can you please get me like the fire department or something? And then the operator behind the scenes has a little table there and looks up the number of the fire department and then connects them, right? They don't even need to see the number. They just give a name and then it gets allocated. Or vice versa, maybe like when they want to come up with a number, like I don't think this is how it works, but like they could be like, hey operator, I would like to have a new line. And then for my company Bowser factory or whatever. I have minor things, so Bowser came to my mind. And then they don't even tell you what the phone number is. They just know that if you tell somebody to call the operator and ask for Bowser factory, it's going to go to you, right? So there's no control over the numbers there. That's kind of the same thing that's happening here, okay? So that abstraction, we're about to kind of get rid of it, because now we're going to take a little bit more control of how memory gets allocated and deallocated. We're going to be able to, whereas before, when you want to create a variable, you have to do that at compile time. You have to define, so far, if you've done things right, you have to tell the computer when you're coding it at the coding time, like I need this variable to be created. You can't do that at runtime, okay? So you can't have two pieces of code. In one of them, you create a variable, and one of them you don't, and then just like let that happen at runtime, because it knows, it has to know ahead of time so it can allocate it. Even if you don't use it, it has to allocate it, okay? Now we're going to change that. And the big change is going to be when it comes to arrays. Right now, all of your arrays have to be done at compile time with a fixed size, which is not very optimal when you don't know how much. So if you want to make a program that reads information from a file and that file varies in size, then you don't know how big you need it. And if you make it too big to be safe, you could be wasting a lot of space. The ideal thing is to read it in, count how many spots you have, and then make it that size, and then read it again to copy the information, and then you're being optimal with space. Maybe not with time, because you have to read it in twice, but we're not in 302 talking about time complexity so far. You'll get there someday. So with all said, now we can go back to what I would have otherwise started this video with, which is just like what pointers are. But you tell me in the comments if you think that this introduction helped you to better motivate you and better kind of set the scene before we talk about pointers. So let us begin. All right. Okay, so pointers. The first thing I want to show you is how to create a pointer. Okay, so to create a pointer, the syntax for that is you're going to say data type. You're going to use the asterisk key, which is, if I look at my keyboard, you just kind of do it without thinking. It's on the number 8. So you gotta, I guess, hold shift and press 8 to get the asterisk done. Or if you have a numpad, then you have actually a key. But I don't know anybody that actually would code and use the asterisk from the numpad. That'd be weird. But hey, you're free to do that. Okay, and then from there, you put an identifier. Okay, so what is this asterisk called? I mean, does this have a technical name? Well, great question. It does. It does have a name, and it is called the dereferencing operator or indirect operator or indirection operator. Okay, so let's go ahead and write that down. So the asterisk is properly called the dereference operator. Okay, or the other name you might see it by, again, I am a fan of giving you as many variations of the names as possible so that you don't get lost if you hear one of the variations and you're not aware what it is and you're like, huh. It's like, imagine they were calling classes somewhere like potato and you're like, oh yeah, make a potato. You're like, what? You're like, yeah, make a potato. Like, what? But then if you know that some people like to call classes potato, then you're good to go, right? I don't think, by the way, anybody calls classes potato unless the class is representing a potato and then they have an object called potato. Then I guess that would be legit. Okay, so all right, so you know that the asterisk is called the dereferencing operator or indirect operator, but you probably have no clue what either of those terms really mean, dereferencing and indirection, right? So don't worry, we're going to go a little bit further, and we're going to say that what it's really doing is it's referencing to the object that to which like the operand points, okay? And by that I'm saying like that is the pointer, okay? So in other words, the asterisk there is the job of it is to create a pointer, okay? So just think of that for now, but also when you're using it other than for creating pointers, you're using it to dereference something or you're using it to access what it's pointing to, okay? So let me just write that first and then we'll go right into the examples, okay? So I'm saying this refers to the object to which the operand, in other words, the pointer, points to, okay? So let's go ahead and create a pointer. All right, very cool. So to do that, the first thing I'm going to do is, let's just make it. Let's just make a pointer. Just full send it. So you got an integer pointer. We're going to call it P. Very original, P for pointer. Okay, so as you can see, this little pointer has, as the syntax said, a data type, the dereference operator, and an identifier. In this case, the identifier is just the letter P, the data type is integer, and the dereference operator is just the asterisk, which is just, it's just a thing, right? You have to embrace that as being a special keyword, I guess, in C++. So why do pointers have data type? In C days, there was a thing known as a void pointer, which didn't have a data type, which was flexible. The reason why pointers have a data type will become clear as I show you how the memory is handled. So for now, all I want to say is that it needs to know how big whatever it's pointing to is, okay? And also it needs to know what it is so that it can actually use it, okay? Because like at the end of the day, everything is zeros and ones, and particularly in memory, everything is stored as zeros and ones, right? That's what I was saying. So ultimately, those zeros and ones can mean a lot of things. They can mean numbers. They can mean floating point notation using the special system. They could mean an ASCII value for like strings or just cars. So they can mean a lot of things, right? So to know what they mean, they need to know what it is that representing. So when you make a variable, that's why you say, this is an integer variable, because then it is able to translate what those binary values are into what the type is. Otherwise, it's like trying to print out an integer as a float. It will just print out weird garbage numbers. Or if you're trying to print out an integer as a string, and it's just going to be a mess, okay? So, all right. So we have a pointer. Very cool. Let's go ahead and make a normal variable just to compare it and see what that looks like. A normal variable would be something like int x gets 25, right? Okay. So we can see the difference between a pointer variable and not a pointer variable. But more importantly, let's make the pointer do something, you know, like poke it until it does something kind of thing. Let's make the pointer point to our variable, to our x. How do we do that? Well, we can do that by using the assignment operator on the pointer variable p. So we're saying p gets, and then instead of just saying p gets x, we are going to be putting an ampersand in front of it, okay? Now, what is this ampersand? You're like, whoa, 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 what is that? Is that like AND logic from like conditionals? I'm like, not in this scenario. In this scenario, the ampersand has a special definition, and that is known as the address of operator, okay? So the ampersand is the address operator. Address of operator. I don't know if you put a hyphen there. I'm not gonna put it though. Okay, so whenever you see an ampersand, you call it the address of operator. So if I'm reading this line out loud, what I'm really reading this is as p gets address of x. So pointer p is getting the address of x. Now, what am I talking about by address? Well, that's why I spent the 20 minutes talking about this stuff. It's getting the address, the hexadecimal address of wherever in memory that variable is being stored. So when I say, you know, if you think about over here like RAM, when I say int star p, so when I make that pointer p, that pointer itself requires space too. That's a variable too. So somewhere in memory, let's just say address 100, which again is in hex. Somewhere in there, I say, okay, this is going to be what p is, and the operating system will remember that's stored there. Okay, what's stored there right now? Just like any variable, it's not initialized, so it could be just a garbage values. Okay. Then I say, okay, make another variable, and this time we're going to call it x. Well, that one also takes 4 bytes, so it's going to take an entire row. But again, maybe this one's at address 311. Okay, you have no control of these addresses right now. Okay, this one though, you are initializing, and you're putting a 25 in there. In binary, but it's 25, okay? What this third line of code is doing, it's saying, okay, I want you to take the address of X, which is going to be this address right here, 311, and I want you to assign that and put it on P. So now, instead of there being garbage here, we actually are storing 311 in hex. Okay, so maybe because it's hex, let me put this 0x3. So we're storing that address there. So now pointer P contains the address of X. Why is that important? Because now we know where X lives per se, and so we can access it and play with it and modify it. And you'll see in a second, okay? But ultimately, just know that what you're doing here is you're storing the current address of X in pointer P. Okay? Now, here comes the cool part. We all know that if we set cout X, that we would get 25, right? Because it's just a normal variable. Right. What happens if I say cout asterisk P like that? Well, this is actually going to print out 25. Okay? So when I say cout and I use the dereferencing operator, I am dereferencing pointer P. Dereferencing is like unwrapping or unwinding where P is pointing to. So in other words, I'm saying, get me the contents of whatever P is pointing to. Dereference that. So in other words, if I just said cout P, I would get 0x311 printed, because that's literally what's in P. It's just a number, which happens to represent an address where X is, but it's just a number at the end of the day, a hex number. But again, it's just binary, right? But if I put the asterisk in front, if I dereference it, now I'm saying, okay, I don't care about what P actually contains, which is just an address. I'm saying, go to the address that P contains. So go to address 311 and then get me the contents of whatever is there, which is 25. That's kind of where the word indirect operator comes in. It's indirection. So it's like going to whatever it's actually located at. Okay? So there's no problem you can't solve by adding another level of indirection. It's a famous quote. So that's kind of one of the big powerful things of pointers is you can create alias variables. So you now have two ways of accessing the content of X. You can access them via X itself, but you could also access them via your pointer because it's pointing to X too. But it doesn't stop there. It doesn't just stop at accessing. If I now go ahead and say dereference P gets 55, like asterisk P gets 55, this is actually going to do the following. It's going to go into whatever P is pointing to, which is 311. So whatever 311 address is, which is X, and actually modify that. So from this, in fact, let me just copy and paste this. So from this, what this line of code is going to do is it's going to replace the 25 with a 55. So I'm saying, what's P holding? Well, P's holding 311. Okay, well, because the asterisk is here, I want you to dereference that. So go to that address of 311, go there, and then set whatever is there to 55. Okay? So again, this is going to go ahead and store 55 in the memory location pointed to by P, which happens to be X. Okay? So to refresh, the asterisk operator is known as the dereference operator or indirection operator, and it has two uses. The main use, first, or I guess the first use I showed you, is to create pointers. You just put it before, like, you know, that's the difference between this and this, is literally the fact that I have an asterisk in one of them, right? So if I don't have the asterisk, it's just a normal variable. But if I put the asterisk, it's a pointer variable, okay? So you create pointers that way. Then you have the address of operator, okay? The address of operator is going to allow you to dereference or to find out what the address is, not the reference, to find out what the address is of a variable that you pass in. So in this case, the address of X. Okay? In other words, I should write it here, is the ampersand is going to be a unary operator that returns the address of its operand. And it's important that we remember that it's doing this, because don't forget that, like, I could write this like if A is equal to B and C is equal to D, right? Like, I know this is valid C++ code. Well, I mean, don't forget to put the rest of the if statement, but still. Like this, in this case, this is an AND. So it's logical AND, right? And then I believe you also have, although I'm not 100% sure, but I'm like 99% sure. I haven't done this in a while. But you could also do bitwise AND, I think, if you use a single one, right? I think. So that's a binary operator. But this is a unary operator, and that's why there's no ambiguity as to which operator you're referring to. It's kind of like a little bit like plus plus, right? So like A++, this is a binary operator, but it's using the same symbol as the, A++ is a unary operator. In this case, it's post increment, but it's using the same symbol that like the binary operator of addition uses, right? Except it's using two of them together. Vice versa, the minus one. Actually, even the single plus can be a binary operator. It's rarely ever used, but like technically speaking, I could write something like this: A equals plus 5. And that is literally just the same thing as writing 5. It's more kind of to match if you do A equals minus 5, because that actually means negative 5. So in this case, the plus and the minus there are unary operators. But in the case that you do something like 2 plus 3, or you say something like A 2 minus 5, in those cases, they're going to be binary operators. So C++ has, there's only so many keys that you have access to in a keyboard without having to do special symbols, like special or extended keyboards. So they have to reuse some of these symbols in different ways to be able to do as many operators as possible. And one of the ways that you can clearly organize that is by having some that are unary and some that are binary, and there's no ambiguity for the compiler to be able to understand which one you are using in there, okay? So that's what the ampersand does, and that's why it's a unary operator. And then, of course, going down here to the second use of the asterisk, it's going to be when you're dealing with a pointer variable to dereference that pointer variable, and then basically saying go to whatever the pointer is pointing to and then play with that. So in this case, I am changing it to 55, but I can also afterwards, if I say cout x, then this is going to 55. It's going to print out 55. So basically overwrote the 25 that we had in there, okay? And similarly, I could also print this out again by saying p. And then it'll be the same thing, so 55. So that's your introduction to pointers. Next, let's go ahead and do an example in a class. Okay, so pointers are not just limited to single variables like built-in variables. You could also have class pointers. So let's just go ahead and make a simple struct. We're going to call it student type, just st for brevity's sake. And we're just going to have a single variable in there, but this could be again a class. We call it GPA. So it's a class that contains some variables, and one of them is GPA. Okay, and so in your main code, if you want to make an object of the student class, all you got to do is say the name of the class and then an identifier. Okay, right? Cool. All right. What if you want to make a pointer that could potentially point to an object of the student type class? Well, the same way. So you have your data type, you have your identifier, but the difference being that you're going to have that dereferencing operator in there. Bam. And make sure it's stuck to this, like there's no space there. Just for formatting's sake, so it doesn't get confused. Okay? What this is doing is making a pointer variable, so it's not a student type variable, it's a pointer variable, okay? It's just all pointers are pointer variables. They have different data type, which means that they can point to different things, but they're inherently the same, which is just literally a point. All a pointer variable is an address that you're storing there. And that address, all addresses are going to be the same size because they have to fit it in memory. If it's a 32-bit system, that size is going to be 32 bits. So it's the same thing as an integer size. If it's a 64-bit system, then it's going to be 64 bits. So it's going to be like a double in terms of size. And all pointers are going to be the same. Why? Because it wouldn't be good if you had a tiny pointer that could hold only like the first few addresses, and you're like, oh yeah, but I'm only going to use it for these addresses, so I should be okay. That's really bad and dangerous, and it's just like, no, you don't want to go there. So they're just like, okay, all pointers can hold all addresses that are available, so we just make them all the same size, make it all consistent, less prone to errors and weird bugs, etc., etc. Okay. So in this case, we're going to make a pointer variable, and it just happens to have a type st, as in like it's only meant to point to student types. Like you shouldn't point it to other things, otherwise bad things can potentially happen. I will take those words back when we talk about up and down casting, but we're not there yet. So we're quite a while from there actually. All right. So now we have a pointer and we have a variable. What if I want the pointer sptr to point to the object that I created, the line above it? So that's student. Well, it looked the same thing as before with the integer. It's just in this case we're using class names, but that's pretty much it. So we're saying assignment, the pointer s or sptr pointer gets the address of s, like that. All right. So again, this is basically storing the address of s in sptr. So again, if we have our memory, somewhere in here is going to be s. It could be kind of big because it has to hold also the double and whatnot, blah, blah, blah. And somewhere else, again, we don't really have control right now of these things, is the pointer sptr. And this pointer has some garbage, but the moment that we run the line address of s here, and when we run this line, now whatever this address is, I would say 11, well, maybe just address 10 for fun. Well, these are all, they're multiples of 4, so there should really be multiples of 4. So we'll do 16, which is a multiple of 4. So what this is going to do is it's going to copy 16 there, which is 10 and 10, 10, 16. And then it's going to be pointing to that. Okay? So far it's the same thing as with the integer. Where it's going to get a little tricky and why I'm showing you this example is when we want to access the members. So, to access members. How do we access the members? Okay, well, first let me show you how you would access it normally. So like, if you just have a normal variable, like the way, normal class, the way we've been doing it for a while, we know that all we got to do is put the class name, or actually not the class name, the object name, in this case s, put the member access operator, which is the dot, and then from there we put the name of the local function or variable, or sorry, class or member function member variable. So in this case I could say s.gpa, right? So I can like see out this, assign it, whatever I want. So I can say s.gpa gets 4.0. All right. So I can do it this way, no problem. The question now becomes, can I do the same thing, or how to do it properly for a pointer variable? You might be inclined to say, oh, well, all I got to do is this. Let's say you want to update it to 3.9 because they didn't understand pointers properly, so they lost some points on their test. You might say like, oh, okay, all I got to do is just put the pointer variable, put the member access operator, and put the member variable name, GPA, and call it a day. Unfortunately, you got two problems here. Number one, remember, SPTR is a pointer. If you're trying to access what it's pointing to, you need that dereferencing operator, right? That's why when we see out it before, like the P, we needed to put the dereferencing operator before it, right? When we are assigning it, we need to put the dereferencing operator before it. So similarly here, that's your first mistake. You gotta put the dereference operator. The second mistake, the one that's gonna scare you, give you nightmares, is that this is still not gonna work. Why? Because now you run into a different scenario. Technically speaking, you are in the right path per se, but there's a problem here, and the problem here has to do with the order of precedence. Okay, let me write that just in case you can't understand me. Order of precedence. What am I talking about? Think back to the good times, when you were in elementary school, elementary school, maybe middle school. I don't know. You're learning about order of precedence between different operators in math class, right? We all know that if I say something like 4 plus 2 times 3, I can't do a 3. We all know that in this scenario, this multiplication has to happen before the addition, right? If you do the addition first, well then, geez, you gotta go back to school. But you shouldn't, because order of precedence says multiplication operator has higher precedence than the addition operator, right? And so you go in and you sort of make a list of operators, and you typically go something like the highest priority is going to be, there's actually one above that, but yeah, exponents. And then you have like multiplication and division. So like multiplication, division, addition, subtraction, and so on, right? But higher than that, you have, of course, your parentheses, right? And so on. So that same concept has to be applied in C++. I mean, it is applied because when you're doing math in C++, it has that order of precedence. But it also has to be applied within internal operators of C++. In this line of code, you are actually using multiple operators, right? You have things like the assignment operator here. You have the member access operator here. And you have the dereferencing operator there. So you have 3 operators right there, okay? So which goes first? Well, it should be obvious that the last one that is going to be this one here. Why is that obvious? Well, because this stuff needs to be cleared out before you can assign anything. It's like these guys got to duke it out and see who's going to go first between them, between the asterisk and the dot, who's going to go first. And then when they finish fighting, then you want to assign 3.9 to whatever that resulting address is, right? So let's understand what is supposed to happen here, okay? So if we look at memory, the class variables, when they're stored in memory, well, a class in general when it's stored in memory, what happens is, if you have a class with multiple variables, what ends up being is you usually just put them all together. So like, let's say we have a class A, and it has like 3 variables in it, which are X, Y, and Z. What ends up happening is class A is going to have a spot for X in this order, spot for Y, and a spot for Z, and they're all kind of going to be bundled. You don't know where in memory, because again, when you create the object, it just goes anywhere in memory, but they're going to be together. And typically, the address of A is just the address of the first member of A. So like this is also the address of A. So like one of the cool things to see is like you want to print out the address of a variable in your class. It's more than likely going to be the same address as the actual object itself, as long as it's the first variable listed. And that's a little foreshadowing. We can take advantage of this sort of feature to access private variables when we shouldn't, but yeah, we'll play with that at some point. Okay, so what I'm getting to here is that the order matters. And when you're trying to use a pointer, like SPTR, and let's say SPTR is pointing to class A, like this specific object of class A, which you can call lowercase a, the pointer is just going to point to the beginning of the class. Okay? So if I'm making an object of A by saying AA, somewhere in memory, we have the slot right there that contains our class. And this could be address 0x10, okay? And that represents this specific object of A. And somewhere else in memory, I could have another object of A. So maybe I do like A2. And maybe that's down here. That is also technically split into X, Y, and Z. But A2 itself is the first part of it. So it's also pointing to the X, right? So if I make a pointer for A, so if I want to make a pointer for A, I'm going to say something like A PTR for pointer. If I say PTR gets the address of, sorry, no asterisk there, gets the address of A, let's call this A1 just to make it clearer. Then what is happening is I'm getting the address of 100 here, okay? So if what I'm really trying to access is the Z in here, once I have the address here, I still need to figure out where in this box Z is. Again, behind it, we don't really see this while we've been doing it so far. We just, it's so nice when we access a local, a member variable from a class. We just call it by name. We're like, hey, give me the GPA from student. We don't care how it's organized or where it's stored in that sort of slot of memory, right? But really, somebody has to know, and somebody needs to be able to organize that, and so that's the operating system's job. But you got to help it out in a way, because when you're dealing with a pointer, it needs to know, okay, the pointer is pointing to the beginning of the class, but where in that class allocated space of that object is going to be what you're trying to reach. And so when you say the member access operator, and then you put in the name of the variable you want, that's really an offset to the address that is equivalent to the location of the variable within that. So if we have here X, Y, and Z, if X or A1 is located at address 100, then Y would be the immediate one beneath that. So that would be 104, and then Z would be 108. So technically Z exists at this address. So there is a shift of +8 between the address of the class and the address of the variable that you want from that class. So when you're writing yourself something like a1.z, what's really happening behind the scenes, it's saying, get the address of this and add +8 to that, and then you're good to go. But that's all happening behind the scenes. You didn't know about it, but it is happening. And why do you need to know about it now? Because when you're dealing with pointers, you better know what's happening or things will go wrong. So we'll go back to the student example, but let's just wrap it up with this one. If now that I have this PTR here, if I want to say PTR Z, like that, and I have my asterisk, and I want to assign 10 to that or something, what I really want to do, my expectation versus what I get, is I want to get the address 100 from here, and then I want to add the 8 because of the Z, so that this then equals address 108, right? That's what I want. What I don't want to happen is I don't want to try to first add the 8 and then go to address 100, right? Because like PTR itself is an address, right? So like imagine PTR being like living somewhere here. So like somewhere down here is PTR. So like address 500. There's PTR, right? And that contains the address of 100 in it. What I do not want to do is I don't want to get address 500 and then try to add 8 to that and then try to dereference address 508 and go there to find out my value of Z. That's really wrong. Let me repeat that again as to how I got that 508. The asterisk here is the dereference operator. The job of that is simply to say, take whatever number I'm getting and go there. So like technically speaking, if I wrote something like, I don't know if this would compile, but if I wrote something like this, what this is saying is go to address 208 and print out what's there. Well, I mean, if I put this in a cout statement or something, okay? So in here, this part of the code is basically saying, go to that address. I want that to happen before I do the addition, because I want the +8 to be added to whatever this address returns. I don't want the +8 to be added to the location of PTR and then go to that address, because in one system I'm going to get 108, in the other one I'm going to get 508, but this is the one that I want and this is not the one that I want. Okay, so there's my order of precedence scenario. I want the going to address 100 to happen first before I try to do the shifting to find out the specific member of the class that I want, of the object that I want. Well, here's the problem. In C++, the member access operator, the dot there, has higher precedence. Or sorry. No, I'm correct. I stand correct. The dot has higher precedence than the asterisk. So if you just leave it as it is now, without parentheses, the asterisk will happen first. So this will happen first, and then the dot will happen. Okay? Hold on. Did I say that backwards? I said that backwards. Damn it. This will happen first, and then this will happen first. There we go. Yeah. So the dot has higher, I was saying it right, but I was drawing it wrong. The dot has higher precedence than the asterisk. But that's no good, because we want the asterisk to happen first. We want to go to wherever SPTR is pointing to, and then from there add the +8. Okay, we don't want to add the +8 and then go there, because that will break it. We're going to get an invalid address where it's not what we want. It's going to be containing who knows what. That's the worst part. We don't even know what's in address 508. Like, there could be anything, and it's nothing good. And one of the things you should know is that when you try to access an address that does not belong to your program will probably crash, because the operating system's like, you're not supposed to be here, so I'm going to shut you down. And then, bam, you crash. That's the equivalent for crashing. So that's actually a good case scenario. If for some reason you were to access an address that you do have access to, that's probably even worse, because now you're modifying your own data and you're reading wrong data, and like, there's no winning scenario here. Okay, so we want, again, to have the dereferencing happen first to SPTR, and then to have the dot. So just like in math, what do? Well, we add parentheses to change it. Okay, so it's like in this scenario here, what will be the equivalent mathematical representation of this? Actually, what I have right here is literally would work. Yeah, so like we have literally 4 + 2 × 3, but we want the 4 + 2 to happen first. So how do I solve it here? Very easy. I put parentheses around that, and it's solved, right? Similarly here, to solve this, all I gotta do is put parentheses, and the problem is solved. Now, why did I just spend so long going over something so simple as parentheses? Because, trust me, this is one of the things that the majority of people struggle with, is to understand that with parentheses, and by result, their code crashes. But here's the good news. You don't have to fully, you should, but you don't have to fully understand it, because there is a solution to this messy code. And I'm going to get there in a second. But I'd like to kind of take it a step further before I go there, okay? So we know that doing this is going to solve it, because this is going to get address 100 first, and it's going to go to that address, because SPTR contains address 100. So this is basically like saying, like, go to address 100. Okay, I'm done with that. Now, +8 it for this. In this case, though, because GPA is the only variable, it would actually be +0. But plus it to whatever GPA is. And now we're at the spot that we want to be at. Okay? So just for an example, and again, I'll code this in the next video. Today is all about just like really drawing. We'll code some examples in the next video. But just for the sake of the argument here, suppose that you had aggregation and composition in here, okay? meaning that you have a class A, and in class A you have some class B. So actually here, we have a class A, and then we have a class B. Okay? So in class B, you have an object of A, but you have a pointer to that. And I know I haven't gotten to dynamic allocation yet and all of that, but just for now, just bear with me on this, okay? And in A, we have some int x. Okay? Normally, if there are no pointers used here, if this was just like clean, so like, no pointers used, this would look something like this. If you make an object of B, you say b.a.x, right? So we know that's how we access that variable. Cool. What if this was a pointer and it was using pointers? What would happen then? Well, let's say B was pointed to by something called bptr. So we would have to use the same concept as before. So we have to add an asterisk, we have to use the parentheses, we have A. But because A is also a pointer, you have to add its own set of asterisks, and then your own set of parentheses, and then a B, or sorry, an X. And so on. It kind of grows. This is nasty, particularly because if you look at it without parentheses, and I tell you like, oh yeah, go in and add the parentheses, you're like, oh snap, where do I add parentheses? Well, you gotta add them here, and then here, right? So you come up with the top one, right? This can get really nasty with inheritance, with composition. If you go three layers deep, it's gonna have another set of parentheses and another asterisk in there. And you gotta keep track of this. For me, I see this and it's not hard because I've done it for a while. But I've seen a lot of students struggle. In fact, one semester I made it an extra credit question in the exam to do this like level 3 layers deep. And like very few people got it right. So very sad. But that's why I like to kind of emphasize it now. I'm trying to make sure everybody understands it. But again, why did I say that this is not super critical that you know? Because C++ is cool enough to avoid us this headache right here. Someone's going to come to the rescue. And that rescue, by the way, one time this was literally the end of a lecture, and then I said, I'll tell you next class. But this time we can actually introduce it in this class. Our savior, cue the Superman music, is going to be the arrow operator. Okay? So, what is the arrow operator? The arrow operator is a friend. The full name of the arrow operator is actually known as the member access operator arrow. So, or arrow member access operator, I suppose. We know that the dot is technically, even though we don't say the word dot, is the dot member access operator. We only really say this part, but now I'm going to start using the dot because now we know the other one. The arrow is just known as the arrow member access operator. So, as the name implies, it's a member access operator. So it's used to access members of an object, a class. The difference between the dot and the member, though, is that the arrow is specifically used when dealing with pointers as objects. So class pointers, essentially. So going back to our example above with the student, so this one right here, copy paste it. This right here, let's get rid of the colors for now. This right here, under the usage of the pointer, the arrow pointer, sorry, the arrow operator, would just become that. Look how clean that looks. No parentheses, not even asterisks, just one awesome arrow. Going further to the example up here with the headache, this one, on the other hand, if you're using the arrow operator, would look something like this. Also very clean and simple. So yeah, oh, by the way, if x was a pointer, you would also need to put that asterisk on the outside without a parenthesis, but we're not making it a pointer yet. So, but yeah, at least in this example, it would just become that. So I don't know about you, but that saves you a lot of parentheses headaches. You know, for me, whenever I think parentheses, I think of Scheme programming language. But since I'm not coding in Scheme, I don't expect to have parentheses headaches. So yeah, I'm really happy about that. Okay. So to conclude, well, not to conclude, but to wrap up the discussion with the arrow versus the dot, let's just go ahead and write a couple of things. First of all, in C++, the dot operator, I'm going to say the operator, just a member access operator dot, has higher precedence than the dereferencing operator, which is the asterisk. That's why we need parentheses. And to avoid it, because we don't like thinking a lot of parentheses, so to avoid that syntax, we can use the arrow operator. Okay? Now the arrow operator is literally going to be like your you know, like looking at a keyboard, like next to the 0 key you have the dash, and then you have your next to the M you have the less than, and you have the greater than, so like 2 keys over, and then no space in between them. So I guess you gotta use 2 symbols, but hey, it looks like an arrow, so that's a plus. That's always nice. Okay, so that's your arrow operator. I have this little note down here. I wonder if I can copy paste it. No, I don't have it. I'll just write it manually. I have my TLDR, or I guess it should be too long didn't watch. So TLDW for this lecture. Well, actually no, because we also talk about pointers. But at least for the arrow versus dot, is going to be to access members of a structure, I guess, or class, use the dot operator. To access members of a structure or a class through a pointer, emphasize, oh, that's erased, through a pointer, use the arrow operator. Okay, so that's your rule of thumb, like your words to live by. Okay, and you get to see lots and lots more examples of this. Okay, I'm going to cover one last thing really quickly, and then we're going to wrap it up, and then next class we'll talk about dynamic variables. Okay, so the last thing I would like to cover for this is how to initialize, or how should you initialize pointer variables. So remember, C++ does not do any automatic initialization. So I mean, if you've been keeping up with the series, you have seen in the last video that we we created a class and we were running the debugger, and we could see that some variables are not initialized, right? So I mean, like, it's been proven. They're not initialized. They can be, but they don't always have to be. So you gotta play it safe and initialize your variables, okay? So with pointers, it's even more important than number variables to make sure that you always have control of what is in a pointer. Why? Because if not, if you end up going somewhere where you're not supposed to because you dereference a pointer that was pointing to a garbage location, that garbage location is going to be translated to an actual address. And that address is going to probably be something that does not belong to you. And like I said, the operating system will typically terminate your program when you try to access an location you don't want, which is short for or long for crashing. Worse yet, even if you do happen to have access to it, it's just weird invalid data that you don't expect. You could also overwrite, like imagine that the operating system didn't stop you from accessing, or if you worked around that. You could overwrite other programs' code with your code. So like your code is bad enough now that like not just to break your own code, but now you're breaking other people's programs that are running on a computer because you access their memory location and change this. So like you go in and set up your int x equals 25 and you're running that over your Firefox like code, and now that's crashing too, right? So that's what the operating system's like. Yeah, okay. You can break your own code, but don't go and break other programs that are running at the same time, okay? So it's really, really, really important to initialize pointer variables. But what do you initialize them to? Like a pointer is just an address, and pretty much every single address is going to be valid, right? Well, technically yes, but no. It turns out that we have a special address that we like to use to indicate that a pointer is currently pointing nowhere. And that way, you can check it to see if it's pointing to that address, which represents nowhere, and you know that it's not something you should go to or dereference. What is that going to be? It's just going to be 0 or null, okay? So, if I make a pointer, and I would like to initialize this pointer, I can do it just like other ones in one line, or I can do it in 2, so let's go with 2. So I can initialize it to 0 like that, just like with a number, hard code. Or I can use a special keyword in C++, which is all uppercase, which is null. Null is, I believe, at least null itself is the exact same thing as 0. It's just a keyword for 0. If you're using C++ 11, you do have a third option, or C++ 11 or later, and that's lowercase nullptr. This goes a little beyond just being 0. It's a special thing. I don't really want to talk about it too much, but know that there is a difference. While I guess it's okay to mix and match these two, although you really shouldn't, you should just stick to one of them. I would just stick to this one. I would actually discourage you from doing this, because like people might think this is actually a normal variable and not a pointer variable because they see a number, so they're like, oh, it's just an integer. When it's not, it's a pointer variable. Big difference. So I'll discourage you using that one. I would just say use this one. However, if you're coding in C++ 11 or later, you are able to use this one, but please do not mix and match these two. Not just from a like code should look nice perspective, but like you can run into some weird errors and issues with that. So don't go there. Don't keep your code clean and stick to one of them. I don't care, by the way. CodeGrade might, but I don't. Okay, so really you can think about it as like it being set to 0. And by the way, the number 0 is the only, I should write this down actually. When it comes to pointer variables, they're very picky about what you can set them to. They'll let you set them to addresses by using the address of operator. And as we'll see when we actually try coding some of this stuff, you are not allowed to manually set a pointer variable to like a specific address. So you can't do like p equals 55 if p is a pointer. Why? Because that really doesn't make sense. Like in the examples I gave you above, where I said like 0x100 was this location, this 0x100 was decided by the operating system when I kind of did this line of code. If I rerun the code again, I could get a completely different address from the operating system. In fact, I probably will. There's no control over that. And so it makes no sense for you to hard code an address when you don't have the right to, because that's something that the operating system decides what addresses you're going to get this time around. Next time you run it, you will get different addresses. You just have no control over that. So you just can't automatically assume that you're going to have an address. It's a bad assumption to make. Bad things happen. Even that explanation is an oversimplification between virtual and physical addresses. But for now, I'll just stick to that. And again, they'll kind of you'll relearn some of this stuff when you take 219 and 370. Okay? But just know that you are not allowed, and it's for your own good, I guess. You're not allowed to assign direct addresses to a pointer variable. There is a way around that if you're trying to debug and trying to work out some other problem and you just want to test something. You can pass the flag, I believe, f permissive. That's one of your compilation flags to G++, and you can get around this issue. Okay, not issue, but this limitation. However, again, only for debugging purposes should you do this. By no means should you have this be a required flag to actually have your code compile when you're turning an assignment in. You will probably get a 0 because we will not use that flag to compile it. Codeware won't use it. And then your code will definitely not compile because, well, you can't assign variable directly. You'll get an error. I'll show you that error next time so you can see it. Like I said, I'm a fan of showing errors because then you actually can recognize them and not panic when you see them because you know what to do. You have that experience. Okay. Workaround. I still want to show you the workaround because, it's somebody tells you something, you're not allowed to do something, the first thing you should think about is why and whether that's a good thing to do or not, right? So, and if there is a way around it, and there is, you just shouldn't really do it, but it's there. Just great power comes great responsibility, okay? So yeah, that's really the last thing that I wanted to cover is initializing variables. Now, how can you check whether a pointer variable is initialized? Very easily. Before you touch a pointer variable, so like before you say something like cout p, this is dereferencing p, right? So this is saying go to address of p and then print out the contents. Obviously, if p is an invalid address, this will crash or give you just really weird data if it doesn't crash. So what you usually do when you're dealing with that kind of stuff with pointers is you put this in an if statement that checks if p is not equal to, and then use nullptr 0 or no, or just null. Again, my preference is null. I would discourage you from using 0 and just sticking to either null or nullptr, but don't mix and match throughout your programs. So yeah, this is the most basic of checks when you're dealing with pointers is you just write an if statement before you actually dereference a pointer, checking whether that pointer is null. And as long as you initialize your pointers to null, then this will protect you from accidentally accessing something when you shouldn't because it's uninitialized. This is not the full story because what if at some point like p was valid but now it's not? And we'll talk more about that next time, but what if it is valid at some point and no longer it's not? Then this could fail and you could end up with something like a dangling pointer, which we'll mention again next time. So I would say that using null is not just limited to initializing a pointer variable, but if at any time your pointer variable is no longer to be used or no longer points to a valid location, you can go back and set it to null again. So that way it's cleaned up. And then you can keep using your if p is not equal to null before you access it to protect yourself. You might be like, I too like to live dangerously. I don't need these protections. But trust me, if you don't do this, you will just unnecessarily crash your program and spend a lot of time debugging unnecessarily because you wanted to save one single check, one line of code. Heck, this could be, this could even be this, you don't even have to add extra lines of code. You could literally just throw this in like right here on the side, like put it there and then be okay. But you do you, but don't come to me asking for help. And then I see that you didn't even check for null, right? Because I'll be very mad at you. But I will say this. If you do run into a situation where your program crashes, and it's probably due to pointers, debugger will help you because you can monitor the value of a pointer to the debugger, and then you can see that if your code is crashing on a specific line dealing with pointers, you can take a look at that address and see if it's what you expect it to be. And if not, then you've found your issue. So this isn't per se that this is going to stop your program from being wrong, because it'll just not run this line of code, but it's still going to be wrong. it's just going to prevent your program from just like hard crashing at a spot. So it's not to say that this will solve your problems. It's just going to make them less bad, but still have issues. Okay, just like you want to more gracefully fail at this point than just like hard crash. So yeah, now I'm done. So last video, a little long. This one's last video a little short. This video a little long, but we did actually cover quite a bit today. Like I said, next time I'm going to continue talking about pointers. Specifically, I am going to start looking into dynamic variables and allocating and deallocating memory. So lots of cool stuff to come. So thank you all for watching, and until next time, stay safe.